Good evening, everyone. Welcome to Astronomy Toronto. This is a special live 2-hour version of Astronomy Toronto. This on the day after Voyager 2 passed by the planet Uranus. Over the next 2 hours, we'll be showing you the latest pictures sent back from Voyager as it passed around the planet Uranus yesterday and sent back the pictures today. We'll be looking at all these pictures, talking about the planets in the solar system, comparing them to the planet Uranus. We'll find out a lot about what we've known up until now about this strange planet and what we can expect to see in the next few days as Voyager sends back more of its secrets. We'll be possibly looking at pictures as they come in live. There's a possibility you and I will see pictures the first point in time that anyone else in the world sees them, because Voyager is transmitting these pictures back to Earth. So if any of them come up, we'll be showing them to you. We've got some scientists here in the studio who will be talking to about Uranus, about the Voyager spacecraft, and about these results that are coming in. Also, hopefully, we will be talking to some scientists who are at the Jet Propulsion Laboratory in California, who have been watching these pictures come in, and they'll be able to tell us some of the first-hand results and stories. Trying to do some real live science, because this is the first time anyone has seen such clear photographs of both the planet Uranus and some of its moons. We're going to go to a live shot now. This is coming in right now. This is a picture of one of the moons of Uranus, and boy, don't ask me what it is. We have, it looks like one of the outer moons. It might be Oberon. That is Miranda. That is the moon Miranda going around Uranus. And this is another picture of Miranda. These pictures came in within the last hour. We're not expected to see such clear views of these moons. We'll be going back to them as we go through the show. Well, I'd like to introduce you to my guests who are with me tonight here in the York Mill studio of Rogers. Ian McGregor from the McLaughlin Planetarium, who's certainly no stranger to Astronomy Toronto. Thanks for coming today, Ian.
Thanks for having me, man.
And happy Robbie Burns.
Oh, thank you very much. It's a great day.
And beside him, Dr. Tom Bolton from the University of Toronto Astronomy Department, who has also been on Astronomy Toronto several times before. Thanks again, Tom, for coming along.
It's a pleasure to be here. This is a very exciting time.
It really is. We're really up. All the pictures coming in are just beyond anyone's imagination. After following the Jupiter and Saturn photos, Uranus is really turning out to be an interesting planet and interesting moon system. Well, the Voyager spacecraft, the one that has just passed Uranus, is one of 2 spacecraft that were launched in 1977. We've got some slides of the Voyager spacecraft. We'll take a look at what it looks like. This is the official seal. The idea was that the Voyager spacecraft would be launched, the 2 of them, and they'd both fly by Jupiter. That happened in 1979. They both flew by Saturn in between 1980 and 1981. The fact that it was possible that one of them, Voyager 2, could be swung with a gravitational slingshot towards Uranus and then towards Neptune in 1989 was just a coincidence of the positions of the planets. This is the Voyager spacecraft. The big white dish in the middle, that's how it sends its radio signals, its pictures and whatever, and it's got computers and television cameras on it. The interesting thing is that these spacecraft are traveling out of our solar system, and on the side of the Voyager spacecraft is a record which has music on it and digitalized photographs, so that if any civilization picks up Voyager in our galaxy millions of years from now, who knows if it'll happen, then this is a signal that we from the planet Earth sent out this spacecraft. The next slide, what we do have is a videotape of what the spacecraft actually looks like. I believe Friday morning it was sent from JPL. We'll give you an idea of what the Voyager spacecraft looks like, the different parts and how they work. So we'll go to that videotape.
Voyager 2 spacecraft. Down here what we have is the main bus. This is where we house the 3 main computer systems on board the spacecraft. And the computer systems consist of a primary and backup system computer. Off to the right here, we have the experiment boom. On the boom, we have the fields and particles instruments. Those are the non-targeted instruments, the low-energy charged particle, plasma subsystem, and cosmic ray subsystem. Over here we have a scan platform. This has all our targeting instruments. We have the TV cameras here, narrow angle and wide angle, photopolarimeter, and infrared spectrometer here. And over on the side here in this little box alcove area, we have the ultraviolet spectrometer.
Michael, very quickly, I know that these are all very familiar to you, infrared spectrometer, photopolarimeter. Tell us a little bit about what this device does and what this device does. This is the photopolarimeter.
The infrared spectrometer, what it does is it goes ahead and measures the heat being radiated off the planet and gives us a infrared picture of the target it's at. The cameras themselves, we have a 200 millimeter lens and 1500 millimeter lens. The photopolarimeter goes ahead and gives us other data that is associated, and it's all integrated together to give us the full characteristics of a target. The platform itself is designed to slew, what we call slew, that's the movement of it, by the attitude control computers which are housed in the main bus. We have slewing in two directions. She can rotate in an azimuth direction or an elevation direction. By doing this, by commanding the scan platform to do this, along with using the attitude control thrusters on board the spacecraft to roll, pitch, and make movements and roll, pitch, and yaw, we're able to target the scan platform instruments.
We've got about 20 seconds left. Just tell us a little bit about the power supply of the Voyager 2.
Power supply of the Voyager consists of 3 RTG, radioisotope thermoelectric generator canisters, which produce 400 watts of electrical power that run all the computers on board the spacecraft and the transmitters and receivers and all the scientific instruments. In a nutshell, that's about what we can cover here.
Well, we'll go back to our slides and we'll see that the Voyager spacecraft is quite an incredible machine. Here's a view, again, giving you another aspect of the camera boom on the left and the nuclear reactors on the right, and of course all the computers are in the main housing. Next slide, we'll see basically the routes of Voyager 1 and Voyager 2. They both flew by Jupiter and Saturn. Voyager 1 was sent out of the solar system. Voyager 2 went on to Uranus, January 24th, 1986, which was yesterday, and then it will pass by Neptune 3.5 years from now. The next slide, we see the planet Jupiter. Tom, what are we looking at when we see this photograph?
Well, we're seeing clouds from incredible convective activity and very rapid rotation wind currents on the planet. On the lower left-hand corner, you see the Great Red Spot, which is an incredible storm system. It's much larger than the planet Earth, and there are a number of smaller storm systems there that are long-lived, hundreds of years. Another example of the same thing, I think this is Io maybe, seen in projection against the Great Red Spot, and lots of very turbulent cloud activity. The winds currents on Jupiter are very complex and unusual compared to the Earth.
It's a view of the Great Red Spot, which is sometimes visible from Earth, isn't it, Tom?
Oh yes, it's certainly visible in a telescope. It was discovered around the time of Galileo and has been visible to some degree or another since then.
There's a couple of other spots apart from the Great Red Spot. There's 3 other spots that are white in color.
That's right.
But they're smaller, much smaller than the Great Red.
This is a black and white version of the red spot, which gives you an idea of the detail the Voyager spacecraft sent back in some of its pictures. And these are cyclonic. They turn around. This was a discovery at Jupiter, discovered by Voyager, a ring around the planet Jupiter. You can't see it from Earth, but there is a ring around the planet Jupiter, just like the planet Saturn. The moons, Tom. Tell me a little bit about these, the Galilean moons.
Well, they're essentially a small solar system, Randy. The inner one, Io, is the most volcanically active planet in the solar system. It is a rocky body, and as you go out farther, Europa, Callisto, and Ganymede, you have progressively more water in the planet, and they become more like the Jovian planets.
This is the outer moon of the Galilean moons, Callisto, and you can see that the surface is totally covered with craters. If you added another crater, you wouldn't be adding one because you'd just get rid of as many as you placed on the planet. Totally covered with craters. And the next view, we see a color view of Callisto, and it looks like a big impact on the left-hand side sent shock waves out, just like somebody cracked a crystal glass.
Yes, but notice that you don't see a lot of relief there. You see the circular pattern, but the crust has rebounded and smoothed out, which indicates that you're dealing with an icy crust, perhaps even with a liquid water layer below that.
The interesting thing, too, is the white spots, they show up newer craters, right? Anything
that's
that is
right.
white tonight that we'll see is new on these moons. The darker part is older material. In towards the planet Jupiter, moon Ganymede. Again, whiter areas and darker areas in this color view. And in the next close-up here, we'll see, again, interesting patterns, some streaks and craters in different types of terrain.
Yeah, each of these moons was a different world, unlike anything we've seen elsewhere in the solar system, and that's been a pattern that has been repeated throughout the Voyager mission.
The next moon in is Europa. This is the one of 2010 fame. Very smooth surface with cracks. It looks like an eggshell that somebody dropped. Again, taking a look at these cracks. But there's not much relief here, Tom. It's smooth surface.
That's right.
Like a billiard ball.
Like a billiard ball.
Incredibly smooth for bodies of this size.
And there's the idea that there might be an ocean underneath this ice layer.
Yeah, there's some that have even suggested this may be one of the better places in the solar system for life to have formed.
First of all, realizing, too, these moons are about the same size as the Earth's moon.
Right.
This is one of the most remarkable of the bodies in the solar system. It's Io. It's a volcanically active body. In fact, this circular, semicircular area you see in the lower right is a volcano. Here you see a volcano at the upper left projected against the sky. There are dozens of volcanoes on the planet, some of which are incredibly active. Here you see lava flows on the surface, probably of sulfur, and the entire surface of the planet's being resurfaced on a period of hundreds of thousands of years.
The next place that the Voyager spacecraft visited was Saturn, an incredibly beautiful place. Before the Voyagers went out to Saturn, only thought there were 6 or 7 rings. Once they got out there, they saw 1 million rings going around the planet.
Saturn's a fantastic planet. It's something that amateur astronomers are very familiar with looking at through their telescopes, and professional astronomers have looked at Saturn, but we never expected what we were going to find when we got there.
This is a color-enhanced view of Saturn, and we'll find that some of the pictures we're looking at from Voyager, the computers have a lot to do with the image. They've made them different colors here based on different brightnesses. So you can see maybe there's different compositions or different altitudes in the clouds. That right?
Certainly is, yeah. And compared to Jupiter, which is very colorful, looked like something that you might do in finger painting class, with all kinds of complicated clouds and everything. The face of Saturn is much more bland. It doesn't have all the marvelous features. There's nothing like the Great Red Spot, for example.
Getting closer to Saturn, we saw the atmosphere in this next slide. We'll show you the clouds on Saturn, and yes, there is a little red spot.
There is a tiny little red spot. That's right. It's not as big, and we do see a few bands there, but we're not seeing all that complicated structure that we saw when we looked at Jupiter.
Okay, in our next shot, we'll see a close-up of Saturn, and again, Ian, exactly what you said. It's a butterscotch planet, not pinks or browns or bright colors, and not many cloud structures.
Not very much swirling clouds. It just basically looks kind of very bland. There's a few bands here and there, a few little small features, but nothing like Jupiter.
Well, here is what we came to Saturn to see, and that's the rings. And just the ringlets among ringlets were discovered.
Saturn's great glory is its beautiful rings, and not just 3, 4, dozen, 100 rings. There's thousands of rings. It's almost like the grooves in a phonograph record.
Here's something that was interesting that they discovered. You see those dark markings, they look like shadows on the rings. They call them spokes, and the idea was that there was material which was rising up above the rings, and they rotated with the rings. You were able to see these hour to hour rotating around the planet. Very interesting and very mysterious. Now we get to some of the moons of Saturn.
Yeah, the moons of Saturn are very distinctive in their own right, in the same way that Jupiter's moons are very distinctive. Again, we're looking at objects which are mostly made up of ice. They're not really very rocky worlds, but they have craters on them, and a lot of the different features that we saw on the moons of Jupiter. Here's Mimas, which is often been referred to as Darth Vader's Death Star, with an enormous crater on it. This is a relatively small moon as moons go. It's much smaller than the Galilean moons of Jupiter. And this large crater was formed by an impact of some object hitting the moon. If the object had been larger, it would have probably broken the moon apart.
This was an interesting moon, Titan, which was the only one in the Saturn system that had an atmosphere, and there was ideas that we could look for life here. Ian, what was the result?
A lot of people were looking. They thought there might be some kind of life. They thought possibly with the atmosphere surrounding this moon, there might be some kind of a greenhouse effect, so it'd be warm on the surface. But when they went by and studied it, it turns out that it's very cold. It's about 200 degrees below zero. Not a very good place to look for life.
Yes, but the atmosphere is the closest to the atmosphere of the Earth of any of the planets.
That's
in terms
right.
of composition, density of the atmosphere, and so on. It's a very unique world in that regard.
It's a world we'd like to study a lot more of.
We certainly would.
The next slide we have will show another moon, again a close-up of a moon called Rhea, and again you see the result of the cratering process that went on several billion years ago. We have craters on our moon, there are craters on Mercury, there are craters on the moons of Saturn, and as we found out today, craters on the moons of Uranus, which we'll see later on. Interesting aspect of the rings. You've seen in the space shuttle things float around. It's weightless. Well, things are weightless out around Saturn. But why don't the rings float away? Well, they think it's because of two little moons like this. There might be these shepherding moons, moons that are in orbit around the planet, which hold these small rings in place. And that's something that we're looking for at Uranus, to see if there are these shepherding moons holding the rings of Uranus and Saturn in place. A view looking back at Saturn, just an incredible photograph. Really the photograph of the century, and as the Voyager passed by, it saw it from the top, and another Voyager saw it from the bottom, which gave interesting aspects of the ring material. Some light goes through when looked from the top, some light reflects in different ways, and you see different views of the planet. And that's it for our slides of Voyager. Now Uranus is the first planet that was ever discovered using a telescope. All the planets up to the planet Saturn are visible with the naked eye, and the ancients were able to follow these planets as they went through the sky. Uranus is not as bright enough to see with the naked eye, or it is just at the limit of being able to view it with the naked eye. But using naked eye, it would only look like a very faint star. And Ian, you have some slides tonight to tell us about Uranus and its discovery and who its discoverer was.
Well, interesting enough, we're very close to an anniversary of the discovery of the planet Uranus. It was found on March 13th, 1781, so it's about 205 years ago that the planet was discovered. It was discovered by an amateur astronomer by the name of William Herschel. He was observing from Bath, England, and he had a 7-foot telescope, Newtonian type of a telescope, as telescopes go. And he was out observing in his back garden, and he was studying the stars. He was a very, very fine manufacturer of telescope mirrors. And here we have a picture of William Herschel. He was more or less undistinguished before his discovery of the planet, but that made him famous very quickly, and he quickly joined the ranks of the greatest observers of all time. He was out observing with his telescope in his back garden, and he spotted this object, and he initially thought it was a comet that he had spotted, and he observed it over the next 4 nights, and then he noticed that the planet, or this object, was moving. They tried to calculate an orbit for it, and they found that rather than this being the orbit of a comet, they were looking at an orbit that was much more circular, and the best explanation was a planet. Herschel wanted to name the new planet after the King of England at that time, George III. He wanted to call it George's Star. But I suppose astronomical reason came along, and instead they named it the planet Uranus. Uranus was the father of Saturn in Greek mythology.
And the grandfather of Jupiter, I believe.
And the grandfather of Jupiter, that's right. So that just keeps up the mythological context of the names of the planets.
So it's like a family tree as we discover more planets.
Practically, in a way, as we go along. Now, since that discovery, he became very famous and joined the ranks of the great astronomers of all time. More recently, in 1977, Herschel's house, or the house where he lived in Bath, England, was purchased by the William Herschel Society. Here we have the front entrance of it, and Phil Moselle on the left is one of the active members of the Toronto Centre of the Society. This house was purchased by the Society, and you've got all kinds of artifacts describing the Society and describing William Herschel. And here's a picture in the back garden, and Phil Moselle is standing pretty well in the same place where Herschel's telescope was set up the night that he discovered Uranus.
Must have been an interesting night. They depict him out with his telescope between 10 o'clock and 11 o'clock. He saw it, and must have been quite exciting to discover.
It must have been quite something. Of course, he thought it was a comet, and it took a long time before it was actually verified what kind of an object it was.
Okay, let's move on to the next slide. And in this slide, Ian, you tell us, I guess this looks like what you'd see through a telescope looking at Uranus.
We're looking at some of the moons of the planet. The planet itself is overexposed in this picture, and we can see several of the moons. Uranus appears as sort of a greenish point of light in the sky when we look at it through a small telescope. And here we have an artist's depiction of the planet, the very thin rings around it, the dark rings, and of course this greenish appearance that we often associate with the planet as seen from the Earth.
Now, these rings were discovered just recently, in 1977.
1977 they were discovered, and quite a marvelous feat that they were discovered at that time. It was not thought that Uranus had rings, although people thought there might be a possibility of it. And they were discovered almost by accident. They were observing a star, which was near the planet, and as seen from the Earth, and they noticed the star's light dimming, and from this they figured out there were 9 rings.
It's an interesting effect because that's the way that they found out more about the rings of Saturn, because as Voyager passed over the planet, it looked at the starlight as it passed behind the rings and was able to get very, very good detail down to see how big the rings were within several meters. And I believe that's what they've done just over the past few days at Uranus too. They've had an opportunity to do it 3 times. Watch the starlight as it passed behind the rings, and it would flicker, and that would tell you if the material was as big as a refrigerator or as big as a house or whatever.
These are so-called occultation experiments.
Occultation experiments, right. What do you have in the next slide, Ian?
Okay, the next slide I think is showing us a picture that was taken in 1984 of Uranus. It's showing all 5 of the planet's moons, or known moons at that time, and it's also showing the dark rings that are very, very close to the planet itself. A computer-enhanced image. There's also a star image in there as well. Perhaps one of the interesting things about this picture is when we look at Uranus, we're looking more or less from one of its poles, and so we're sort of looking down on the planetary system, and here we have the 5 moons.
And this is an artist's depiction of maybe what one of the pictures we'll see later on of the behind the planet of the rings around Uranus.
We're sort of showing a phase of Uranus, and that's something we would not see from the Earth.
Right. Oh, and that's the end of those slides. Well, the next few slides we'll look at, we'll talk a bit about Uranus as a planet. Again, it's the 7th planet going around the Sun, and later on we want to compare it to one of the to Earth and the kind of rocky planets that we have in our inner solar system. But as Ian mentioned, Voyager spacecraft is moving in towards the planet more or less from the North Pole, because Uranus is tipped on its side, and that has caused scientists so many problems with things like magnetic fields being tipped and all these other problems, and it looks like you're moving right in a big bullseye as the Voyager spacecraft is moving in.
It's like an arrow coming in towards a big bullseye with the rings and the planet and the moon system.
Now, Randy, you say it causes problems, but it's also a great advantage, because one of the things you want to do at Uranus is study the atmospheric behavior. And here we have a world which is a great contrast to the Earth, where the seasons last for very long periods of time, with the sun sometimes overhead at the North Pole, sometimes at the South Pole, sometimes at the equator. So it gives us a laboratory with contrasting conditions for the Earth, which is very important for constraining models for climatology and meteorology.
I think we'll see that in our first slide in this set, Tom, which shows the orientation of the planet. Again, this is what we're looking at from the Earth. A few moons there pointed out with arrows. The next slide, we will see the view that Voyager would have. It looks like it's coming down on the planet. And here we see 5 of Uranus's moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Worlds that up until now look just like little stars through telescopes. Now we're beginning to see them as real distinct worlds. This is what we believe the inside of Uranus would be like, Tom.
Yeah, we really don't know. About all we know is that it has a high content of relatively light elements like hydrogen and helium, but the composition of the planet is more a guess based on what we know, what we think we know about the formation of the solar system.
But there's no way, of course, we can get inside, or it's
There's
just...
no way we can get inside, and in fact, there's some real controversy right at the moment about the composition of the planet. Some recent observations suggest that it has much more helium than was previously believed, or as a reasonable person would believe. And we're really looking forward to the observations of Voyager to test that result.
Yeah, interesting point. It just came in today that they were thinking that 40% of the planet was helium. It's now been moved down to 10%.
That's a more normal
That's a more
number.
normal.
That's
Yeah.
a much more comfortable number, but then leaves a set of ground-based observations to be explained.
Right. That slide that we just had up there now, we'll go back to it, which gives you an idea of what we're looking at with Uranus. The planet is tipped on its side, so instead of like the Earth being like a spinning top and going around the sun, in a sense, Uranus is rolling around the sun. It's been tipped on its side, and so on the right-hand side of this slide, you see that the North Pole is pointed towards the sun, so the northern hemisphere would have 42 years of daytime. You move 42 years to the left, and you have the southern hemisphere getting 42 years of daytime. So instead of having a few months of night and day as we do on our poles, Uranus has 42 years of night on one side, 42 years of day on the other, going around the sun once every 84 years.
There's also one of the puzzles about the planet, too, because we don't understand why it is tipped so much compared to the other planets and their rotation axis.
Yeah, not only don't we understand why it's tipped over, but even harder to understand is why the moon's orbits are also tipped over.
Why would they tip if Uranus was collided? Why would they tip with it?
That's right. That is an extremely difficult problem to understand.
In our next shot, we have, I believe, a picture of Uranus and the trajectory of the Voyager spacecraft going through the system. And the interesting thing is, with Voyager going to Jupiter and Saturn, it was going parallel to the plane of the moon, so it had a long time to look at all these moons spinning around. But in that slide there, you see that it passes through the system so quickly, within 12 hours, that there was so much work for the satellite, the probe, to take pictures and data.
Yes, and it was harder because there wasn't as much light to work with either.
Only about a quarter of as much light at Saturn, so the exposures had to be longer, and the imaging, the longer distance meant that the radio signals were weaker too by the time that they got back to Earth. Okay, let's look at our next slide, which shows if you were on the Voyager 2 spacecraft, you would have seen Uranus in the left-hand side of the frame there at 12 hours before encounter. The middle frame, that's what you would have seen 1 p.m. yesterday afternoon, and then 12 hours after that, you would have passed by the planet Uranus, and you would have seen that view there. So very, very interesting view passing behind the planet. And one interesting experiment was, as it passed behind, it sent radio signals back to Earth through the rings, and with that, the signals were somehow examined, and it told that the ring particles are anywhere from grapefruit size to basketball size particles. Very fascinating.
Yes, that's a surprise, I think, a bit, because the other planets, Jupiter and Saturn, that have rings, the particles tend to be very small. So there's a contrast here between the characteristics of the rings of the two, which goes along with the fact that the rings of Uranus are very dark, whereas the ones, both Jupiter and Saturn, are bright.
Tom, we're about to look at our first set of pictures. Could you explain briefly how pictures on Voyager are sent back to Earth? There can't be any film involved. They can't get it filmed back to us to get it processed.
No, it's done with what amounts to a kind of television camera, except the signal is recorded digitally, and in most cases it's recorded on tape. And then after the where a satellite's done its work, the tape is played back, the signal is radioed back to the Earth. I believe the radio transmitter has a power of something like 22 watts. So it's not your 50,000 watt radio station out there. And the signal comes back very weak to the Earth, where large radio telescopes record it, and the digital information then goes into a computer where it can be processed. Various adjustments can be made to the signal, and we'll see some of those, I think, later in the program, to enhance particular features that you want to see, or take very low contrast images and make them higher contrast so you can see detail. and then that's what we see up on the screen.
Now, a color image is a different story.
The color image is a much tougher game because it's not a color camera. What it does is take pictures through different colored filters. So it will take 3 pictures through different colored filters, send the 3 pictures back, and then those are combined in the computer. It records a color chart each time it takes the picture, so the computer knows how to recombine the data. But there's an additional complication because the satellite moves between pictures, so there has to be adjustments made to put these images together, because between the pictures the satellite took them from slightly different positions.
Well, I think we're ready to see our first set of pictures. These are put together from Thursday, all day Thursday. The first pictures we really got back here at Rogers. This is a picture of Uranus, and again, the information that Tom was talking about was on the right. Here is one of the moons. I believe this is Miranda. A long exposure. Those aren't stars, that's just noise. This is interesting. A color picture of Uranus on the left, and an enhanced version showing that the reddish area is a warmer area, and that's close to the pole. And it's what you would expect. The warmest area is the area facing the sun. One of the moons, Thursday, we didn't get a lot of detail from the moons. They were just too far. We're working on just the limits of the Voyager camera.
Yeah, you're really seeing these as we would see the moon with the naked eye from the Earth.
First, good views of the rings. There are several rings seen here, and again, they vary in brightness, they vary in width, and again, just discovered in 1977, but now this is our first close view at the rings of Uranus, which we believe are in different size particles.
Very thin rings,
Very
too.
thin,
Yeah,
compared,
that's incredible.
just not like Saturn whatsoever. Another moon, getting closer to the moons, which we actually passed by close the other day. Looking for rings. We're looking for new rings, looking for new moons, and actually just announced today a new ring. The 10th ring was discovered, and also a new satellite, and I'm beginning to quickly lose count of all the satellites. all the
Somewhere
moons.
around 14 or 15.
That's right. Must be up to 15 if there's another one now.
Yeah. Again, a view of one of the moons. We're thinking that these are icy, right? Icy worlds.
They should be at this distance. Certainly the ones of Saturn were icy, with one exception.
Here, a view of the rings, and again, it's fascinating to see them come in. We actually saw these come in as they came down from the Voyager spacecraft. And the interesting thing is Uranus is so far away that with light traveling, or radio waves traveling at the speed of light, from the time that Voyager sends out the signal to the time we receive it on Earth is 2 hours and 44 minutes. It's just incredible. And you have to wait. Once a picture is taken, you have to wait that long to see the results on Earth.
It's interesting to see the arrangement of those rings. Very symmetric.
Here's a view of the rotation of Uranus, and you can see a cloud just at the top around the equator, which was something that we don't know the rotation period of the planet.
This will be one of the most important results from the mission, because we need to know the rotation period in order to model the interior of the planet and really to find out what it's made of. And we have not known the tremendous uncertainty about the rotation period of the planet up to now.
The estimates are ranging somewhere between about 9 hours to 20 is kind of
20,
popular
24
figures.
has been as high, but the consensus has been homing in around 15 to 17.
15, yeah, somewhere in that range.
Yeah.
But if you're seeing the rotation of clouds on a planet, I mean, if you were taking a picture of the Earth over a period of time and watching the clouds move, that would not be an indication of the rotation period of the Earth, because the clouds move at a different pace.
That's right. The best example of that is planet Venus, where the clouds rotate in 4 days and the planet does it in something like 243 days, I think, in the opposite direction to the way the clouds go. No, what we'll really be looking for, I think, are the magnetic field results, which they've now found one, I understand, because that should reflect the rotation of the interior of the planet and really be that's the important factor.
So the magnetic field is locked into the planet.
That's right, and that's been regarded as the important rotation rate for Jupiter and Saturn before, where there the clouds move at hundreds of miles an hour in some cases, and the rotation rate you get from them is very different depending on where you look on the planet.
Tell me a little bit about a magnetic field, Tom. If the Earth has a magnetic field, we know that some of the other planets in the solar system have a magnetic field. What is a magnetic field, and how does a planet get one?
Well, we don't know the answer to the last part of that. That's one of the reasons we're interested
Nearly got me there.
in this. Magnetic field is well, the same sort of thing that a compass is coupled to on the Earth. It's produced, we think, by electrical currents in a liquid conductor layer somewhere in the planet. And there are various ideas about it. This is generated as a kind of dynamo effect, we think. Uranus has turned out to have a much weaker field than was expected. It's actually weaker than the Earth's, as I understand the results.
But magnetic field of Uranus is about the same as Saturn.
Is that the latest result? That would be a bit stronger than that of the Earth then.
Yeah, I think
The last figure I heard was a third that of the Earth, around a Gauss.
Well, it varies, doesn't it? It varies at the equator and at the pole.
It depends on where you look.
Yeah.
That's right.
So I think the
That's
strongest was at Saturn, but maybe at Saturn's weakest point.
Yeah, you might be going in the...
right. Yeah, I see.
That's right.
Well, in any event, presumably this has a kind of dipole shape, which means there'll be a North Pole and a South Pole with magnetic fields connecting it, much like a bar magnet. And if that field is tipped over with respect to the rotation of the planet, which in most cases it is, then as the planet rotates, you'll see a periodic variation of the magnetic field, and by monitoring that, you can get the rotation period of the planet.
The interesting thing that they found out just today is the fact that the Uranus is turning like this, but the magnetic field is off a little bit. So as it turns, in effect, the magnetic field is deviating like this every day.
Right. Well, that's not a surprise. In fact, you'd count on that to get the rotation period. All of the magnetic fields for the planets except Saturn are tipped by order of 10 to 20 degrees with respect to the rotation pole of the planet. Saturn's is almost exactly aligned with the rotational pole of the planet.
Okay, what we're going to do now is go one step farther, go to the videotape that we got yesterday as Voyager 2 moved in to Uranus, passed closest to the planet at 1 p.m. yesterday afternoon. Voyager 2 is, of course, a NASA probe, and you just have to be amazed at how well Voyager 1 and 2 have performed. It's 8 years since this spacecraft has left Earth. First it saw Jupiter in this depiction, passed through the rings or through the ring plane, and then yesterday passed right here at the closest point to Uranus. And this is the first clear view of one of the moons of Uranus. This is Titania, I believe. And we can see some markings, a white speck on the side, which I believe turned into a scarp, and you begin to see some craters and some smooth areas and some highlands.
It looks relatively smooth in this view.
The best place to look for detail is on the right-hand side where there's a sunrise or sunset, and you can begin to see some shadows. This is the limb of Uranus, not a heck of a lot of detail.
No, not too much there.
No, there's just no it's not at all like Saturn or Jupiter where you can see detail in the clouds.
No, I think this is not too much of a surprise. We've known from ground-based observations that there was a lot of haze in the atmosphere, and any clouds were likely to be very obscured by this haze.
Once we pass by, you're looking back towards the crescent Uranus, so this is just the top part, and a bit of dropout there in the picture. But again, these are raw images. This is a processed image. This is Uranus. Now you see the red part on the top and the bottom. Well, the upper atmosphere of Uranus is thought to be methane. When methane combines with sunlight, it turns into things like, well, different products, and they believe they're seeing those different products on the planet there. Here is a color version of the rings. False color, again, this is computer processing. What they're looking at is different types of material giving off different colors. The interesting thing about the rings is they say that they give off as much light as coal. In effect, they're black pieces of material, which is shocking to when you think of ice and whatever being so bright.
That's right.
But they may not be made of ice.
Well,
We
yeah,
don't know that.
that's
at this
right.
point.
That's true. Another view of a moon. Again, these are images which just came back yesterday. A lot of what we're going to be talking about tonight, instant science. What can you say about these worlds which we're seeing just for the first time ever? All you can look for are bright markings, dark markings, and I guess we're saying that The brighter markings are probably newer, probably
New craters possibly, or materials come up from the interior of the moon.
a bit of a chevron-shaped feature there, which we've been able to see a bit better today.
Yes.
A bit better. You have to wait for that one. Just incredible
Yes, hang
images.
on, folks. This is really exciting when you see the chevron in detail.
And more rings, bit overexposed. Now we're looking for shepherding satellites. We're looking for new moons. So basically, as the Voyager goes by, it keeps taking pictures all around at different exposures because they don't know what to look for. Just know that they have to point it in a certain direction. Here is an improved picture of Titania pointing at the different features there. Looks like a big basin on the top right-hand side that maybe there was some sort of impact or it dropped down. And then there's that very strange scarp, although it looks like it is a smooth feature, Tom.
Yeah, the impression I have looking at that is there aren't many craters with a lot of relief at any rate. Remarkably smooth body in that impression.
So we're looking at more depressions, very like small depressions as opposed to craters that we see
right,
on the moon.
more like the moons of Jupiter than the moons of Saturn in that respect.
You might see some black images, and we'll talk about them a bit later. Here's another view of a moon. Again, beginning to see more detail, but we're really getting down to the limit of the frame. All the itty-bitty little pixels are beginning to come out, all the little images which are then turned into radio frequencies and then sent back to Earth.
Yeah, give the guys a few days on that at JPL and it'll look a lot better.
This is interesting. You're beginning to see dark material inside of light material. Maybe this is dark material that was deposited at a certain point in time, or
Yes,
maybe...
some of the moons in Saturn showed this dark material as well, which may be carbon-rich material from the interior of the satellite that has escaped
Bubbled up in
outward,
there.
bubbled out, or been brought up by impact puncturing the surface.
Okay, back to some raw images here. And every now and then you might see some black dots in a regular fashion on the screen on a particular image. Those are on the lens of Voyager. They're there for measurement purposes, but they're taken out once the pictures are processed. So they're not black dots in regular fashion on these satellites. Again, getting closer to some of the moons. And Tom, we're going to talk about the information that's on the right-hand side in a few minutes. So just everyone notice the fact that there is some information on the right-hand side, which I guess is for the computer processing later on.
Well, that tells you what the computer has done to the picture. The one on the top is a distribution of the brightness levels on the picture they got, and the one on the bottom is what comes out, what you see on the screen. So when there's a limited range of brightness, they stretch it to a wider range so you can see more detail in the picture. It's called contrast enhancement. And if there's a very narrow range, you can spread it out into a very wide range so the human eye can pick up detail better. The computer can do it, but these are pretty pictures you want to look at. And you want to show to your local congressman and things
right.
like that, so it's important to have them look good.
Let's talk a bit more about computer enhancement. Now, where each individual part of the picture is broken up and given a number between 0 and 255. So
Right. There are several 100,000 picture elements in this, each one which has a number associated with it, which is the brightness that was recorded by the camera. And picture elements is called pixel for short in the jargon of the scientists. And so those numbers come back, and then you can play around with those in the computer, and you can, if you might have a range of, say, from 0 to 255 as a possible number range, and maybe all of your brightness levels are between 10 and 20. So you take the numbers between 10 and 20 and you spread those out between 0 and 255, so you have a much higher contrast. So it's like looking at something through a fog where it washes out all the contrast and then processing it and throwing away the fog so you can see what's in there. It's a wonderful process. There are other games you can play too. You can take a picture that was taken of a spherical object and distort the geometry so it looks like it's on a flat surface, or you're looking at it like this and you can change your perspective so you're looking at it like that from a different direction. Computers are wonderful things.
it's interesting, some of the pictures that came in today, it said at the top, Uranus rings. You know, fine, there are the rings, and there was nothing there. And the scientists were being asked, is this a big disappointment? Said, no, we're sure that the images are there. We just have to as you say, take it into the computer, stretch out the contrast a little bit.
Yeah.
All right, the next part of the program, we'd like to look at Uranus as a planet, compare it to the other planets in the solar system. And Tom, the Earth is a terrestrial planet. That's the term for it.
Right. The planets in the solar system are really broken into two classes. The terrestrial planets, like the Earth, Mercury, Venus, Mars, and the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. Pluto is sort of an oddball that doesn't fit the class. The terrestrial planets are made up of solid bodies, silicon and oxygen, mainly with iron, nickel, metals. The Jovian planets are mainly gases, hydrogen, helium, very light elements. So there's high density solid bodies and relatively low density but very large Jovian planets. I think we've got some slides we can show here. Perhaps we can put up the first slide, which just shows the difficulty of observing Uranus. I think we've already seen that in some of the slides we saw earlier. It's a very small angular size object as seen from the Earth, so we really can't learn much about it except indirectly. And so the great importance of the Voyager mission has been to be able to get close to it, because we've had to learn by induction, really, the properties of these outer Jovian planets.
The interesting thing about these Jovian planets is they're made of, as we'll find out, hydrogen and a little bit of helium.
Hydrogen and helium, which is basically the same composition as the Sun.
Right.
Jupiter is, as far as we can tell, very close to the same composition as the Sun. Saturn seems to have a little more heavy elements than Jupiter, and Uranus and Neptune quite a bit more heavy elements compared to the hydrogen and helium. That's something that we don't completely understand why it should be so. Each of the Jovian planets seems to have a core that amounts to about 15 Earth masses of heavier elements, the kinds of things that make up the terrestrial planets. And then they have varying amounts of hydrogen and helium. Jupiter is very large, 318 Earth masses, a huge object, whereas Uranus and Neptune are more like 15, 20 Earth masses. They have not gotten as these big clouds of hydrogen and helium. That's one of the puzzles about how the solar system formed. We also would like to know exactly the composition between these two, the Jovian planets and the terrestrial planets. Why are the terrestrial planets close to the Sun, Jovian planets far from the Sun? The obvious answer is hydrogen and helium couldn't be trapped by the planets when they're close to the Sun, when the Sun's hot. But when you look at it in detail, it may not be that simple. And so it's important to look at these low-density objects and understand why they are different one from the other as part of putting this whole puzzle together about how the solar system formed. But there are many other differences between the Jovian planets and the terrestrial planets. The terrestrial planets have very low volatile contents on the and mostly on the outside, the atmospheres and water in the case of the Earth, whereas there's huge volatile contents in the Jovian planets. The terrestrial planets have 3 moons among them, all of them strange in the sense that the moon is, our own moon is too large compared to the planet. The ones on Mars are trivial moons.
Probably captured asteroids.
Yeah, that's right. Whereas the moons of the Jovian planets are numerous, 15, 20,
big
typical
families,
sorts of
miniature solar systems in their own right.
Certainly seem to be. Yeah, well, here we have the slides. Here's Uranus and Neptune as seen from the Earth, somewhat weaker exposures than Ian showed in his slides. You can see you can't see anything about these planets at all from photographs. And the next slide shows typical terrestrial planet. Oh no, I'm out of order here. Here are all of the terrestrial planets and Jovian planets lined up so you can see the relative sizes.
Okay, which are which again?
All right, terrestrial planets are the small ones: Mercury, Venus, Earth, Mars.
They're the rocky.
The rocky ones.
Okay.
And then the big ones at the bottom, the 4 Jovian planets, much larger, very low density objects compared to the Earth. They're like, densities are like water rather than like rock. I think the next slide then is shows the relative densities of the planets in terms of the density of the Earth, which is the densest. And you see there the Jovian planets are very not very dense. Now here's a typical terrestrial planet, solid body, got a water oceans, a few clouds, but the basic body is a nice spherical, solid, rocky body.
The interesting thing about the Earth, too, is the size of its moon. So we really can
much larger
say
than we would expect.
The moon is an anomaly. It's an incredible anomaly because it's so large compared to the Earth, and it really stands out.
So in a sense, we're a double planet.
Yes, we are definitely a double planet. The moon is a planet on its own.
This is something, in fact, we sometimes have said kind of offhand here as we've been discussing. We've called some of the moons that we've been looking at worlds or planets. And since we're now studying some of these moons and becoming familiar with them and their distinctive features, they almost become sort of miniature planets to us.
Yeah, they are worlds of their own.
Worlds of their own right.
We're certainly going to see that in some of the pictures we'll see later. Miranda can be called nothing but a world on its own, even though it's a relatively small planet.
Up until a matter of a few days ago, the moons of Uranus were basically just points of light.
That's
Points of
right.
light and just names.
And names.
In mythology.
That's about all we know about them.
Yeah, that's right. I think the next slide shows, we saw something like this before, Jupiter. It's turned over on its side. But you see lots of detail in the clouds. I think the next slide shows a close-up, shows all of the incredible detail you see on Jupiter. It's a warmer place than the planets further out. It does not have the haze in the atmosphere, so you can see the clouds deeper down in great detail. You can see all the incredible wind structures produced by the winds. The next slide, I think, is Saturn. Here you see relatively little detail because there is more haze and the features are smaller, probably obscured by clouds higher in the atmosphere that obscure the deeper down stuff that you see in Jupiter. The next slide shows the kind of detail that you see in the atmosphere of Saturn. This is much less spectacular.
Now, is that because Saturn is colder? Is that pretty well the reason for that?
Well, there are probably several reasons. One is that a lot of the cloud activity you see in Jupiter is deeper down in the atmosphere, and that is hidden in Saturn because there are higher haze layers that obscures it. Part of it is the difference in the structure of the planet, which gives Saturn somewhat less of this convective activity that you see that produces all the clouds in Jupiter.
The bubbling and frothing.
Bubbling and frothing. It's a very systematic bubbling and frothing in Jupiter. If you see movies of the clouds of Jupiter, which were made by the Voyager, you see these clouds are have very systematic motions with respect to each other. And it's important to understand this because it can be related to the meteorology on the Earth. A different case, planets rotating much faster, and so there's energy coming from within the planet that affects the energy distribution, but the processes that are going on that produce these very different clouds seem to be essentially the same as the ones that produce the weather patterns on the Earth. And by studying them, we learn more about what we need to know to model weather on the Earth. So this mission is important it has an immediate practical payoff on the Earth. And I think that's an important point that can't be made too strongly. I think we have a couple of other slides here that show some of the moons of Saturn is photographed mosaic with the planet, so you can, to emphasize this point that there are very rich satellite systems associated with these planets, not one satellite, but dozens of satellites. In this case, next slide. These are different satellites from the moon. They're icy bodies. They're not rocky bodies. They have craters look somewhat different. We have regions that are smoothed out by water flowing onto the surface. Next slide, I think, shows perhaps an example of that, where a lot of the surface has been resurfaced and frozen over. You see some craters at the bottom. This is a characteristic pattern among some of the Saturnian moons, and I think we'll see some evidence of that among the moons of Uranus. I'm somewhat surprised at that, I confess, but it seems we will see that. The next slide shows a smaller moon, Hyperion, of Saturn, 3 different views. This is a moon that's so small it has been broken up and it has not rounded itself out into a sphere, so you see this thing tumbling, and we may see some of that in the smaller moons of Uranus.
So it's been compared to a hockey puck, I think, in terms of its shape.
Yeah, well, people from the United States tend to refer to it as a hamburger, I think. They're not familiar.
We'd refer to it as
That's
a
it,
yeah,
that's right.
rather large hockey puck. Why do some moons turn out round and other moons turn out all jaggedy?
Depends on the size of the moon. If the moon is big enough, the gravity will be stronger than the internal strength of the material, the mechanical strength of the material, and it will round itself out into the least energy configuration, which is a sphere. But if the mechanical strength of the material is greater than gravity, as is possible in these small moons, ones that have radii of 20, 30, maybe even 100 kilometers or a bit more, then you can have very irregular shapes.
So these are the kind of moons that if you took a few good steps, you could maybe jump off. The gravity would be
Yes.
so
Yeah,
so
not
little.
too much, not much mass
That's
to them.
right. That's right.
And some of these moons, too, are, that we're looking at, they're kind of jagged and such, maybe like the 2 moons of Mars, for example, are possibly captured asteroids. They're not objects that formed originally around the particular planet that they're associated with now. They may have been traveling somewhere else out in space and have been captured.
Yeah, that's right. Well, the one we were looking at, Hyperion, is probably a piece that was chipped off another
Some other
moon.
object.
It did not form like that originally.
Well, some of the scarps, say on some of the moons of Saturn, it looks like they actually were hit, broke apart, and coalesced again. They look like they've been attached
Come
together
back
just by
together
their own
again.
gravity.
Yeah, that's quite possible.
I have a question about landing on a Jovian planet. We've landed on Venus, unmanned spacecraft, landed on Mars. What about landing on a Jovian planet? What would happen?
I wouldn't recommend it.
Not very good.
They don't have solid surfaces, at least until you get tens of thousands of kilometers down into the planet where the solid material is, and even then, these are basically atmospheric planets or oceanic planets, oceans of liquid hydrogen down at some depth. You couldn't land on them. You could go in conceivably and float around in a balloon. That's a possible mission, more likely unmanned than manned, but you will never set foot on a Jovian planet.
So the bubble men from Jupiter hypothesis is right out the window.
Not so good.
Not so good. Not so good.
But the other guy might come along and start looking at landing on the moons. The moons have got a little bit more of an interest as far as possibly landing on them.
And the solid surface, certainly.
They have solid
right.
surfaces, and some of those moons are extremely interesting objects.
There is another mission slated to go to Jupiter, and that is Galileo.
Galileo mission this coming May.
It'll be launched
Very
in May.
powerful spacecraft.
And one of the most interesting aspects is they are going to send a probe down into the atmosphere, and it'll just keep going down and send data back. But it should be quite interesting, something to look forward to.
And also, of course, the Galileo mission is not going to be a flyby mission in the same way that, for example, the Voyager is flying by Uranus or when it went by Jupiter and Saturn. It's going to go in orbit around Jupiter and then spend 2 years photographing the satellites and the moons and studying the giant planet itself.
Okay, well, somehow an hour has gone by. We've got 1 hour to go. In the next hour, we'll have the latest photos sent back by the Voyager 2 spacecraft of moons, the moons that Tom has been talking about. He's still surprised that Miranda is so incredibly detailed.
Amazing world.
And we hope to show you that. We hope to talk to another U of T astronomer, Scott Tremaine, who is very active in determining moons around Uranus and how they are shepherding moons in the rings. So we hope to talk to him, and we'll also be asking you to give us a call and give us your comments about what you've been hearing about tonight. And so that's the first hour. We'll be back to you on Astronomy Toronto in just a few minutes.